Consultant with a company called Sama, and I'm here to discuss boosting Tensorflow inference performance using Asyncio. And so let's get started now. So like I said, I'm working as a research engineer focused on life sciences. So Sama, we build life science products for big pharmas, right? So one of the things that we are trying to do is how can we use the latest developments in deep learning, apply it such as NLU and everything, and how can we reduce the time to market for of cancer drugs, right? That's one of the things that we're trying to do. So how that happens is like there is something called clinicaltrials.gov.in. So when FDA gives an approval for human trials on any cancer drug that is under development, what they do is like they go to the data set that is put up in clinicalgov.in. So cancer patients, especially stage 4 cancer patients, go and sign up over there, and they try to match which is the best. It's called cohort solving. So which is the best match, which profile best matches for the given trial drug that they're trying to develop. So this kind of takes a lot of time, and that's the reason why. So the time taken currently is 7 years for a market for a drug to reach market after clinical trials, right? Which is something should not be happening, because there has been a lot of development which we can actually use to reduce it to 2 to 3 years. That's what we are working on. So, so my area of interest is how can we best deploy those models. I mean, you have all these data scientists and everybody, and they are really good at the math and fixing everything, and deploying those, releasing the model that has really good accuracy. But unfortunately, what I get to see is, things are not from the software engineer's perspective. It's not done in the most optimal manner. And why do I say that? So let's take so deep learning models are all built around something called tensors, right? Tensorflow itself, the name itself, tensor. So let's see what a tensor is. Okay, it's basically a mathematical structure that groups vectors together, right? I'll show you an example of this, an image example. So if you think about it, let's take an image of 28 by 28 pixels. Okay. That 28 by 28 itself is a vector, a matrix. Let's say a matrix, right? If it's a color, if it's a color image, RGB, 28 by 28 by 3, right? If it's a video of 60 frames per second, 28 by 28 by 3 by 60. You're getting the idea, right? So that's the reason why you use tensors for deep learning, right? And another advantage of using tensors is that you can actually batch everything. So those who work with deep learning, they'll know something called batch normalization and batch optimization. It always makes sense. So when you're training the data, it's always better to run it in batches. So tensors are essentially an advanced data structure that gives the same mathematical operations like matrix addition, subtraction, multiplication, and eigenvalue eigenvectors on a big chunk of matrices, right? That's the basic idea behind it. But which is fine, which is really good when you're training it and all. But then the problem is when you try to put it in production, right? And Google actually, if you can read it, in TensorFlow serving, there is a small section where Google says that it'll be better if you can actually batch your request, right? And there are a lot of people who actually complain that TensorFlow is is slow in production and all this. That's because they are actually trying to request one sample processing at a time. The thing that is required is you have to actually batch it together, right? If you think of it in that terms of that scale, in batching terms, your user experience is going to come down. You're getting the idea, right? So that's what that's something hit me like. So that's what we were trying to solve. So what we figured out was. The question was how to batch it in production using pure Python. The alternates were to actually use, so there was there's this language called Go. I'm sure everybody has heard of it. it uses CSP. So like you have structural programming for C, object-oriented for Java, and functional for Haskell and Scala. You have something called CSP and actor. CSP for Go, Go follows CSP pattern, communicating sequential processes. Which, if you look at the proper use case of Go, right, you have something called Go routines, right? They are essentially coroutines itself, but I'll come to it. I mean, that's very useful when you want to do batching. And the only equivalent equivalent to Go routines that you have available in Python is Asyncio, right? So I wanted to actually cover actor as well, but then actor is pretty common. I mean, if you think about microservices, they're actually actor pattern itself. So I'm not going to cover much get into much of the details of that, but I'll be trying to show how you can implement CSP pattern, Go style code in Python using Asyncio. No external dependencies, nothing. Okay. The first thing that so let's just quickly cover a few FAQs. Right? The most common question that I get when I talk to people about coroutines and channels and pipes and etc. is, there is this massive question. The first question that I get is, how is a coroutine different from a subroutine or a function? Right? And subroutine is actually a very low-level construct that exists in your assembly code. It does not return a value. It only has a return statement that says, okay, go back to the code which called me. That's all. Whereas a coroutine and function, both are high-level values that exist in the high level, as in within the VM of the language. Okay, do not confuse with that. And one major difference between coroutines and functions is, function has only one entry point and one exit point. So your normal Python definition, you have that calling statement where you enter the function and then you have the return part. Whereas if you were to look at a generator, the generator has multiple each statements. I'll cover that later, maybe it will be better. And okay, and one more thing. What are channels? Okay, so channels are essentially message passing medium. If you want to think of operating system pipes, maybe you can think of that. But then pipes are like an operating system service, operating system level constructs. So the problem with using operating system level constructs like threads or pipes or processes of that, you have to call operating system services that does the respective thing, which kind of slows down things, right? So we want to stay as much as possible inside the Python VM itself and use the Python VM for all those extra, as much as possible use the Python VM itself. And okay, one more thing that I want to cover is, so there are certain things inside CSP. It's called events, then you have channels, then you have interleaving processes, interleaving and interface, a lot of technical constructs of CSP. I'm not going to cover all that because they'll be unnecessary waste of time, plus you might get confused when you suddenly get all those jargons at your face. So, and okay, one more thing is, one major difference between coroutine. So, I'm sure everybody knows that okay, there's one more thing that I'd like to cover that's called operating system services, operating system service called selectors. Okay, so a selector is nothing but a notification manager. Just treat it as a notification manager. We'll get into the details of that pretty quick. Okay, I've just covered this part also. Okay, so here's the thing. So if you notice this, right? So okay, why do the major question to ask is, I mean, why am I considering a coroutine or a generator as a, why is it so special? Okay, the major reason for that is, so if you think about how a function works, a function, it's pretty normal, right? You call a function, it creates a stack frame, and with that stack frame code object, that whatever is a bytecode object is assigned with the stack frame, and then the function executes and the stack frame is popped out of it. That's how the state is managed by Python. Okay, you're getting the idea, right? So if you think about it, the magic with generators is that it kind of can, if you have a yield statement in between, it returns a value. But then, so if you were to think in traditional terms, you're actually popping the stack frame, right? But with generator, it's like it's kind of like magically suspended over there. So that stack frame continues to exist even though it's a stack, that last in first out. You have to get rid of it, right? You're getting the idea? So there is a small caveat, and this is one of the points that I always notice, that people find generators and Asyncio coroutines to be difficult to grasp because they are unaware of the small point, which is Python VM stack is not actually implemented as a stack. It's a heap that acts like a stack, right? I'm sure you would have seen in your data structure classes in college, in your college data structure paper in your college, that you can have a tree that can behave like a stack, right? So that's the same approach that has been done with Python VM stack, which gives you the opportunity to pick and choose which stack frame do you want. That's the reason why something like a yield or an await is able to suspend its state in between. So whenever Python starts executing, sees a yield or an await, it just returns a value what it is supposed to return, and the stack frame is frozen over there. The state of the function, that generator function, is frozen. It continues to persist over there. That's the key point here. So okay, let's get to the point. I mean, I've been explaining a lot of things. So okay, let's get to Asyncio. So what Asyncio does is it builds on generators. The only difference between an Asyncio coroutine and a generator is you have to explicitly call the generator for it to continue, right? You do a next on it. That's when the generator actually continues its execution. Whereas what Asyncio does is, with that await statement, it's actually registering a call. It's actually registering with the operating system selector service. So to notify it. So when it starts executing, it reaches the await point, and at that point it returns the value, and it tells the operating system to notify it whatever it's waiting for. So maybe for a next return, or maybe an external input-output queue to come in, input-output signal to occur. That's what is the basic structure behind it, and that's what is Asyncio coroutine built all around. That basic idea that instead of using just a callback, instead of using just a call, you're using an operating system selector service to invoke it further. And so there are two possibilities with that. Okay, there is this one talk by David Beasley called Generators. I forgot the title of the talk, but in that he is showing how you can create process pipelines using generators. It's a really good talk. And those who haven't seen it, you should see it. It really opens up your mind to what all are possible with just Python. So okay, there are two possibilities you can do with coroutines. One is coroutines will spawn small subcoroutines, and two coroutines can be connected via message passing data structure like a queue or something like that. So we'll see an example of a coroutine spawning coroutine. Okay, if you look at in this example, you see this piece, right? There's a child coroutine, and so whenever this is, I'm using a framework called Scenic. It's a pure Asyncio framework that is actually really fast, and there are reasons to why it is actually fast, which I'm not gonna. So they are using a custom implementation of the loop, called event loop, called the UV loop, and UV loop is actually dependent on a library called libuv, which is used by Node.js. Because of which this thing is actually, its event loop is actually very fast. So, so this is a child coroutine that the parent is gonna spawn. Okay. So for each and here, if you notice, the child coroutine actually calls any batch processing service. In this case, it could be Tensorflow serving or whatever. Okay, so for whenever a request comes in, a parent will spawn a child. So this is using WebSockets, and the child, when the batch processing service responds, whenever it responds, it will via WebSocket it will send back the response to the user. That's the basic crux of it. Okay, let's see how this is actually happening. Okay, this is the parent request, parent method. It gets a request. Okay, and first of all, this is a batch service. This is the future. So we'll get to it quick. And this is the call stack, the Python EM call stack. This is so I'm trying to show how it happens behind the scenes inside Python, using just a simple presentation. So the first request comes in, and okay, one more thing is this batch service, right? It's set to start processing when the buffer reaches 3. So when it gets 3 samples, it starts its job. So you get the first request, it spawns a child, and okay, if you notice the difference in the previous and this one is, in the call stack section, the parent is not existing anymore. The parent so the parent spawns the child and it's not existing anymore. That's all. The job of the parent was to spawn the child. That's it. So the child has been spawned, and the child reaches. So it reaches a section where you call await some batch service, batch processing service. It calls that batch. So this can be HTTP REST call, whatever. It creates a sample there, and the child creates a future because it's waiting for that response to come back, which hasn't happened yet, because the buffer is set to 3. Okay. So C1 is for child 1. That's the basic nomenclature that I'm trying to follow. Goes and child is suspended. So if you see it in the calls, the child is continuing to exist in the call stack, right? And upon the next request coming in, a new parent frame has been formed in the call stack. Okay, and then the same process continues. The parent spawns another child coroutine. The child coroutine is spawned in the call stack. A frame is created in the call stack, and then it requests to the batch service. Another sample has happened, and it registers with the future. It registers a future, and then it disappears. Again, the same thing, the same process, right? So it doesn't make any sense to continue it 3 times. So at this point, what happens is now you have now 3 samples. So let's say the TensorFlow, this thing is set to process for 3 requests. And at this point, TensorFlow starts working, does its job, and returns the values. So these futures are now resolved, right? And because they exist in the call stack, you can actually further continue from the point where it was paused. Okay? So it'll take first C1, C1 will give the response, next, and now C2 has disappeared from the call stack because its job is done. Again C2, and it does the job, and then likewise even C3 and even C3 will go. So it's the same iterative process. So okay, that's kind of that was a part of actor model called supervisor pattern, as in like a parent will spawn multiple small coroutines, which is responsible for keeping track of the state of the flow, whatever flow was happening. Now next is coroutine chains, producer consumer coroutines. So I'm going to show a very simple example. So if you look at it, you have a producer and a consumer. This is, I'm sure many of you might have already seen all this. There's nothing special happening here. Only thing is I'm passing in a parameter called Q, right? And Q is an Asyncio queue. The producer will produce some random values using you'll just iterate over it and put the values, and the consumer will consume and print it. Nothing serious happening here. So the major difference between what I showed previously and this one is, in the previous one, there were multiple small coroutines being spawned, right? In this one, there are only two coroutines, right? One is generating the values and putting it down a queue, and the second one is actually consuming it and doing whatever processing it's supposed to do, right? So there are many coroutines happening. So instead of C1, C2, C3, multiple coroutines inside the stack, you'll have only C1 and C2. That's all. Okay. It does nothing, it just produces and prints the values. So now let's scale what I showed you previously on a much bigger level. So let's try to form coroutine graphs. Okay, this is where things start getting interesting. So let's say your particular, so this I started experimenting with this with this idea. We are actually trying to build a virtual assistant, more of like a bot. So with bots, it's like you have to be able to manage your states in a scalable pattern. And if you think about a bot, right, each user is having a conversation, and conversations can go in any direction, which kind of translates into, so if I were to put it in simple terms, there will be a unique pipeline for each user, right? With a microservice or whatever you have, is like you will have a single pipeline which is common for everybody. In this particular case, you will start having multiple pipelines for each user. So let's see, user 1 is logged in. At that point, he has his own coroutine thing. This is the structure that he's having. I'll show the code also for this after this. But I need to put in the idea what this thing is. So the input comes in. The first, so if you notice in futures, already all the nodes are registered inside the futures and they exist in call stack. The reason being, each node is awaiting input from the previous node. Right. I'll show the code for it so you'll understand why that's happening. So a request came in, node 1 starts processing, and at that point its future is gone. Right, if you notice this. And then it passes the value to the subcoroutines. And to T, okay, the nodes having T are the ones who are actually interested in, who will be calling Tensorflow. So, serving service. So, it starts its execution, it reaches the point where it needs to call Tensorflow, it calls Tensorflow, registers a future, suspends itself, and then passes the Python VM control to the next coroutine. And the same thing happens. It registers callback with the TensorFlow service, and then registers another future, and so it continues. At this point, another user logs in. He is having his own another unique pipeline. Okay, again same thing. Because 2 and 2T and 3T are waiting for TensorFlow to respond, the user A's pipeline cannot continue. So user B starts execution, same process, and then 3T. At this point, so the buffer has reached. So it's now 3 samples are there. TensorFlow starts working. Okay, and in the meantime, the loop is occupied by some other coroutine. So if there is another pipeline that's happening in another user is logged in, he's having the Python VM. So TensorFlow starts working. TensorFlow resolves the results, and then user A's pipeline will continue to work. Okay, I barely have 5 minutes left, so I'll just quickly, I think you get the idea, so if you notice it. So I'll just quickly jump to the code because we have to do. So the basic idea is this, make coroutines do the state management for you instead of using something like a Redis or. So what I get to see is people tend to put the state, whatever you have to store inside a global dictionary, and then, which is kind of a risky thing to do. It will fire up in the long run. So I've tried to package this whole thing into a framework, right? So okay, for now, I'm calling this framework DAE. It's shorthand for directed acyclic event graph. So if you think of it, that coroutine graph which I showed you is a directed acyclic event-based graph because it's waiting on events, right? So directed acyclic event graph, you have something called node. I'll show you. Okay, this is the top node. Okay. You can write any kind of concepts what you want to have. Only thing is you have to do is you have to inherit node and add an output port to it. So each, as you saw in the graph, right? If you're okay, in this one is having 3 outputs, 3 output channels. So that channel, so you are adding an output channel over here, self.outputs.add an output port. And you're just naming it for debugging purposes. And you override this thing, asyndef dunder call, and you're putting this inside. So like you saw that producer consumer example, like in that simple asyndef thing, you put it inside a infinite while loop. And so I have to work out, so this is a work still in progress actually. And so the signal is nothing but that message, right? The signal object is a message that you pass it down the stream. So you just think, and then you create a random value, package it inside a signal, and put it downstream, right? Think of that graph. You're just putting down the value. So there will be. So I'm initializing a graph object, and that graph will have 2 random source output. Then the third part is an adder node. Nothing. It will just take the 2 incoming values and add it. So what I've done is, so you add 2 inputs and 1 output. So because you have 2 random values coming in, add it and out it. simple stuff. Two random generators. The third one will add it. It'll take it, and here's the thing. See, it's awaiting on the input for the input to come in, and then it'll take the signal value and add it. Right? And then it'll send to the printer node. Printer node does nothing, but it'll just simply print it. That's it. So the main advantage of this is, okay, so if you think about it, it's actually small, it's just 3 small coroutines, right? So what you can have is, so you can have really complex logic inside this Dundacall statement, Dundacall method. Because of it, so you can have dynamic coroutine graphs forming depending upon what is your current requirement, right? So if the user says something, you can have another flow. It will modify itself during runtime, and because it's spawning coroutines, it's very light on the Python VM. And so I don't know how many of you attended that dev sprint by Prashant and Raghu. So he was explaining how it is actually very expensive for Python to create objects, right? And so the obvious question is, why is this better than, why is this entire structure better than creating multiple small threads, right? Threads are at the end of the day another operating system service. So when you ask Python to create a thread, it's actually calling the operating system, respective operating system service to allocate memory and create, to spawn threads and get the job done. And at the end of the day, Python is, there's GIL locking everything. So it doesn't make sense to have anything like